Last year, humanity built 48 of the machines that make advanced AI chips. Not 48,000, 48. The newest ones cost $400 million each, the price of a Boeing 747, and every single one came from one company most people have never heard of. Not from America, not from Japan. From a company that started in a leaky shed in the Netherlands. One company decides how fast AI can get. And its grip goes deeper than one machine. It builds the machine itself. It owns the company that makes the light. It owns a quarter of the company that grinds the mirrors. It even decides who gets one first. Every phone, every data center, every AI model you have ever touched passed through its machines. But the strangest part is not the monopoly. The strangest part is that nobody, not America, not Japan, not China, has been able to copy it. This is the story of the most absolute monopoly in modern technology. The engineer who spent 40 years building a machine his rivals called impossible. The light that has to be manufactured from exploding metal 50,000 times a second. And the number, under 50 a year, that quietly sets the speed limit of the entire AI race. This channel covers the machines that quietly run your life and what they cost you. If that is your kind of story, hit like and subscribe so you do not miss the next one. To understand how 48 machines a year became the world's speed limit, you have to start in 1984, in a shed. That year, two Dutch companies, the electronics giant Philips and a chip equipment maker called ASML, spun up a joint venture to build lithography machines, the projectors that print circuits onto silicon. The new company was called ASM Lithography. Its first office was a leaky wooden shed next to a Philips building in Eindhoven. When it rained, the engineers moved the electronics. One of the first men through the door was a young engineer named Martin van den Brink. He joined in 1984, the year the company was born. He would stay for 4 decades, and by the end, people inside the industry would call him the most important engineer you have never heard of. Colleagues describe him the same way, brutally direct, allergic to excuses, carrying the company's entire technology roadmap in his head. Where executives saw quarterly numbers, Van den Brink saw one thing, the next impossible machine, and the one after that. The timing looked terrible. Japan's giants, Nikon and Canon, owned the market. They had the optics, the customers, and the money. The Dutch newcomer had a shed and a first machine, the PAS 2000, that few wanted to buy. For years, the company hovered near death. Philips, its own parent, kept trying to get rid of it. Customers doubted a machine stamped "Made in the Netherlands" could match Tokyo's finest. In its first decade, the company burned money, flirted with bankruptcy more than once, and survived on stubbornness and a handful of believers. What it had was a different way of working. Nikon and Canon built almost everything themselves. The Dutch could not afford that, so they did the opposite. Buy the best part from whoever on earth made it best, and become the company that integrates it all. Keep that idea. It is the whole story. Salvation arrived in 1991 with a machine called the PAS 5500. Finally, a system good enough that the giant's customers started defecting, one skeptical chip factory at a time. It sold, it scaled, and it dragged the company from near bankruptcy to a stock listing in Amsterdam and New York by 1995. The shed was gone. The underdog had a war chest. The real assault on Japan's lead began in 2001. ASML shipped a system called TwinScan, the first machine with 2 wafer stages, so it could measure one wafer while it printed another. Faster output, better precision. The chip factories, the fabs, noticed. The second crack came from a customer. An engineer at Taiwan's TSMC, Bern Lin, pushed a strange idea. Put a layer of water between the lens and the wafer, and the same light suddenly prints finer lines. Immersion lithography. Nikon hesitated. ASML bet the company on it. And through the 2008 financial crisis, while rivals slashed research, The Dutch kept spending. By 2010, the leading edge belonged to ASML, and Nikon and Canon were fading into the rearview mirror. But right as ASML won the war for light, the light itself ran out. Physics presented a bill no lens could pay, and the only way forward sounded like science fiction. Here is the problem. To print smaller circuits, you need shorter wavelengths of light. The industry needed light so short, 13.5 nanometers, that it does not usefully exist on Earth. Air absorbs it, glass absorbs it, a normal lens is a wall. And here is the twist almost everyone forgets. The idea was born in America. In 1997, Intel and the US government pulled the national laboratories, Lawrence Livermore, Sandia, Berkeley, into a consortium to crack EUV light. Washington kept Japan's Nikon and Canon out, but America had no lithography company left to give it to. So in 1999, the Dutch were invited in, on conditions: build factories in the US, share the work. America invented the light. The Netherlands got the monopoly. So ASML set out to manufacture that light at industrial scale. The recipe still sounds made up. Fire a droplet of molten tin, 25 microns wide, into a vacuum chamber at 70 meters per second. Hit it with one laser pulse to flatten it into a pancake. Hit it with a second monstrous pulse that detonates it into plasma at around 220,000 degrees Celsius, roughly 40 times hotter than the surface of the sun. For one instant, that dying droplet radiates the light you need. Now do it again. 50,000 droplets, every second, hour after hour, without missing one. Miss, and the light flickers. Flicker, and a $100 million production run is at risk. And because that light cannot pass through glass, there are no lenses inside. Only mirrors, made by one German company, Zeiss. Each mirror carries more than 100 layers, each just a few nanometers thick. They are the smoothest objects humans have ever made. Scale one up to the size of Germany, and its tallest bump would be 1/10 of a millimeter. The laser doing the detonating is its own monster, built by Germany's Trumpf. It fills a room on its own and pours out tens of kilowatts of invisible infrared power, aimed at a flying droplet 1/3 the width of a human hair. And the whole assembly is so large that delivering one machine takes about 40 freight containers, 20 trucks, and 3 Boeing 747 cargo flights. The buyer does not unbox it. A small army of engineers spends months assembling it inside the fab, and it never leaves. When you sell a machine like that, you are not shipping a product. You are relocating a factory. This is not a lab demo. It is a production tool that runs around the clock in chip fabs. Getting there took 16 years and roughly $10 billion of research. Some estimates for the whole ecosystem run twice that. Nikon and Canon looked at the same physics, ran the same numbers, and walked away. They did not lose the EUV race. They declined to enter it. Behind that one machine stands a hidden nation of specialists, roughly 5,000 suppliers feeding parts into Eindhoven, many of them the only company on Earth that makes their particular part. The monopoly is not a building, it is a web. Then Van den Brink's company did something quieter and smarter. It bought the Bottlenecks. In 2013, it paid about $2.5 billion for S. Weimer, the San Diego company that makes the light source itself. In 2016, it bought a quarter of Zeiss's chip optics division for €1 billion and committed 760 million more to fund the next generation of mirrors. The machine, the light, the eyes, one balance sheet. And the optics deal carried a quiet clause with loud consequences. Zeiss's chip optics division works for ASML, effectively for no one else. Any would-be rival does not just need to build the machine, it needs to conjure a second Zeiss, a second S. Weimer, a second 5,000 company web. That is why the monopoly holds without ever suing anyone. Now, a correction you will hear almost nowhere. Headlines love to call this the $200 million machine. The company's own numbers say the standard EUV system runs about 180 million euros, but the new generation, called High NA, sells for $380 to $400 million, and the roadmap points toward machines costing $720 million each in the 2030s. The price of the machine is climbing faster than the price of anything it makes. But an impossible machine, at an impossible price, from a single supplier, creates a new kind of power. And governments noticed before most of us did. Before we go on, check your own pocket. The phone you are holding, the laptop on your desk, the servers answering your questions. If the chip inside is from the last 5 years, its circuits were printed by light from exploding tin, in a machine you now know by name. You did not choose this company. You cannot avoid it. You are its customer 3 layers removed, whether you like it or not. Count the facts. One company on Earth makes the machine. One company makes its light source, owned by ASML. One company makes its mirrors, a quarter, owned by ASML. That is not a supply chain. That is a choke point. And whoever controls a choke point controls everyone downstream. The company behind all this sits in Eindhoven, a Dutch town most maps skip, and it now employs more than 40,000 people and trades as Europe's most valuable technology company. A town you have never visited, running a machine you will never see, deciding the pace of an industry worth trillions. Washington understood this first. Since 2019, under American pressure, the Dutch government has never granted a license to ship an EUV machine to China. Not one, ever. The most important machine of the century, and an entire superpower, is locked out of the showroom. In June 2023, the wall grew taller. ASML's most advanced immersion DUV machines, the previous generation, now need licenses too. In January 2024, some of those licenses were revoked outright. A company from a small Dutch town became one of the sharpest weapons in a superpower conflict, without firing anything but light. China saw the wall coming and did the only thing left. It went shopping for everything still legal. In the years before each new restriction, Chinese fabs stockpiled older ASML machines by the hundreds, buying time, buying spare parts, buying the previous decade. You can build real chips that way, but you cannot build tomorrow's, because tomorrow requires the one machine that has never been allowed in. Look at where the machines actually sit, and you are looking at the real map of AI power. Taiwan's TSMC alone holds more than half of all the EUV machines ever installed. That is why one island sits at the center of the world's most dangerous standoff. The chips in your phone, the GPUs training the AI you use, their birthplace was decided by where these 40-some machines per year were allowed to land. To make it concrete, the 3-nanometer processor in a current flagship phone and the accelerators inside every serious AI data center physically cannot be printed at scale without EUV. This is not one input among many. It is the gate. And this is where it stops being abstract and reaches your wallet. When AI companies say compute is scarce, when GPU prices spike, when your AI subscription has a wait list, when a data center takes years to fill, the scarcity does not start at the chip factory. It starts at a loading dock in Eindhoven, where the world's yearly allowance of these machines gets divided. There is one more thing almost nobody talks about. Everyone argues about who has the best AI model. Almost nobody asks the question that actually decides the race. The question is, how many can they build? And the answer is the most important number in technology. In 2024, ASML delivered 44 EUV systems. In 2025, 48. For 2027, the schedule says 56 standard machines, plus 10 high NA. Every empire in the AI race, America's, China's, everyone's, is drawing from a pool of fewer than 70 machines a year. That is the world's entire compute budget, decided not by markets or armies, but by one company's production calendar. Every one of those machines is spoken for years in advance. The order book stretches out beyond the horizon, and allocation meetings in Eindhoven decide more about the next 3 years of technology than most parliaments do. The queue is the race. A fab that secures its allocation ships the next generation of chips. A fab that does not, waits. When you hear that a trillion-dollar company is compute-constrained, translate it, they are standing in line in Eindhoven like everyone else. And a system this concentrated is also this fragile. One fire in one Dutch cleanroom, one earthquake under one supplier, one blockade in one strait, and the world's compute budget for the year is gone. We have built the digital century on a single production line. Of course, a prize this large invites challengers. Chinese labs have announced lithography prototypes, and press reports describe ex-ASML engineers and alleged stolen data surfacing in those programs. Researchers are exploring exotic alternative light sources. Some of it may work, eventually. But remember what the moat actually is. Not one machine, but 16 years, $10 billion, 5,000 suppliers, and a light that must be created from exploding tin 50,000 times a second. Copying a machine is hard. Copying an ecosystem is a generation's work. ASML itself is betting the wall holds. The company projects revenue near $71 billion by 2030, riding the same AI boom it quietly rations. Think about that loop for a second. AI needs chips. Chips need this machine. And the machine's maker grows richer the more desperate everyone becomes for what only it can build. The gold rush has one shovel maker, and the shovel costs as much as a jumbo jet. Step back and look at the whole board. America designs the chips. Taiwan prints them. China races to catch up. And all 3 roads run through the same small Dutch town. The only place on Earth both superpowers depend on, and neither controls. There has never been a company positioned quite like this in the history of industry. Standard Oil owned oil. De Beers owned diamonds. ASML owns the ability to make the future smaller, and the machine after high NA, the one projected at $720 million apiece, will only tighten the grip. Follow the chain downstream to your own screen. Fewer machines means fewer advanced wafers. Fewer wafers means scarcer GPUs. Scarcer GPUs mean rationed compute, which is why AI companies cap your usage, why the best models sit behind waitlists, and why a single export decision in The Hague can quietly move the price of technology in your pocket 18 months later. You have been living inside this bottleneck for years. It just never had a name. So the next time a headline asks who is winning the AI race, remember that the honest answer is written on a Dutch shipping schedule. And you are standing downstream of it. Your devices, your feeds, your job, all rationed by a number smaller than a single school's graduating class. So walk back through what you now know. You know the most important machine on Earth is built by one company that started in a leaky shed. You know its light does not exist in nature. It is manufactured from exploding tin, 40 times hotter than the surface of the sun, reflected by the smoothest mirrors ever made. You know not one of these machines has ever been allowed into China, and you know the number that runs the whole race, fewer than 50 a year. You cannot buy one. Almost nobody can. But you live inside their output. Every screen you touch tomorrow was rationed by that calendar. Because the speed of AI was never really set in Silicon Valley. It is set by one company's production schedule, and nobody can stop it, because nobody else can build it. If this changed how you think about who actually controls AI, hit like and subscribe. The machines run deeper than chips, and this channel takes them apart one at a time. Now the comments. A monopoly this absolute, is it the only reason the modern world works? Or the single point of failure that should terrify us? Protect it, or break it up.